Hi, this is Mark. Today we're going to take a quick run through on Apache NiFi MiNiFi C++. On the screen here you see the terminal for building. I'll put that off to the side for now, and then we'll take a quick run through of the actual code base. So I know it's a little small here, but what we can see is we have a number of top level directories. The important ones in this branch are main, which includes our main class. You can see we have code here that represents Windows functionality. We have some code that sets things up and then eventually moves to establish what we have internally called a flow controller. That flow controller handles all the threading, all of the concurrency that exists within the system. It establishes all the thread pools and it runs everything, including your flow. The next top level directory of interest is libMiNiFi. libMiNiFi is the core of our agent. That includes all the libraries that actually do the running. So effectively what we have is this main class that calls upon this API, builds this flow controller, and runs all the functionality within these directories. Now, what I first want to establish is that this is a CMake project, meaning that we have our CMake lists file up here. I won't go through this in depth, but for those who are unfamiliar, CMake is a build ecosystem, and we leverage that with a Bootstrap script to ensure that your system, when you want to set it up via the Bootstrap, has everything installed. That builds the project, including the main class, which is the executable that you will be running, in addition to establishing setting up some of the extensions that are built in addition to libMiNiFi. The extensions include functionalities such as expression language, curl functionality, RocksDB, sensors, TensorFlow, etc. All of this functionality is included per your desires. The reason why we set this up is so that people who don't want to include things such as curl or pcap in their binary don't have to. Similarly, this allows those who want to establish different types of agents or MiNiFi executables to do so pretty easily. So I'll jump over to this is my base in dev NiFi MiNiFi CPP. I'm going to remove my build directory and kind of show you what happens in real time. So the first thing I'll do is run the Bootstrap. That brings up this menu that allows you to select features. So in this case I have persistent repos, libcurl, and expression language enabled. And this is persisted from every run of the Bootstrap, meaning that if you change something it'll save it. So the first thing that I'll do is I'll leave it as is and continue. It's going to ask me for my password and begin to go through all the repos and install all the dependencies. Since I'm building this on my development system that I use for Linux, everything's already installed, meaning that the next step is to run the CMake and it'll do that for us. So I'll say yes and it'll begin to establish what will be our build ecosystem. And you can also have the Bootstrap build it for you, but today we're not going to do that. So I'll go into the build directory. What you can see are all the required CMake portions built, including the make files. And in addition to that, we can see that we have directories for extensions and libMiNiFi. That's because these are all separate sub-projects, CMake sub-projects rather. So that means that if we go over here on the left and we look at expression language, there's a CMake file for that. So when you are writing extensions, you must provide your own CMake, and there's an extension header that kind of gives you some basic extension capabilities and some of the inclusions. So right now I'll start the build process. In this case I just ran make -J12 because I have 12 cores on this machine or this environment. This will run for a little bit. Depending on how many extensions you have set up and established, it may take longer to run. So as we dive into while this is running, I'm going to dive into libMiNiFi. I'll kind of put this off to the side. libMiNiFi is, as I said, it's the core. We have an include, opsys, and source directory in addition to the tests. The important thing to note here is that opsys, for one, has Windows and POSIX related inclusions in them. And include and source directories are obviously the includes and source files. What we have here are a number of directories. We have a core, which has much of our core functionality built into a core package, as we'll call it. We have C2 for command and control. C API are those functions that are abstracting out some of the functionality into C function calls. This allows you to actually create C programs that implement parts of our agent, but these are more library calls as opposed to an executable. If you're implementing this, and there are examples such as in the lib example directory, these are just implementations of an API. So you would have to implement it yourself or use the Python extensions that we have. Going back to the lib MiNiFi directory, controllers or controller services. And then jumping down below core, we have I/O related objects and classes, base set of processors. These are defined in our documentation. Properties, provenance. Provenance is an important aspect of MiNiFi and NiFi. Site-to-site directory, which includes in lib MiNiFi, this is mostly the abstractions in addition to the raw site-to-site. In the extension package HTTP curl, we have HTTP site-to-site for Apache NiFi and MiNiFi C++. And finally, in utils, we have some utility classes that help us throughout the project. In terms of structure, this is the basic layout. We have our core, and surrounding that are the directories that all implement key pieces for various functionality. I think it's safe to say that most users will want more than what the basic package provides, which is a small set of processors, site-to-site, a few controller services. Many of these are, again, within these extensions. There are a number of them: USB camera, as I mentioned earlier, TensorFlow, Windows event logs, and not all of these can run in every environment. So the important thing about Bootstrap is that, and we're nearing the end of our build, Bootstrap has not only bootstraps your environment, but also can help dictate what can and cannot be installed on an environment. Bootstrap is only available on Linux and Mac. For Windows builds, we still have a little bit of ways to go, but those are effectively run by the CMake, and you have to select your extensions. Many extensions cannot be installed within Windows as of yet. We have curl support. I believe there's Kafka and MQTT support, but there's not expression language support yet. So obviously there's a little bit of work to be done for Windows. Windows event log is not something that you will run in Linux, and that's not something that you can build in Linux at all. We've taken a bit of work to kind of abstract these extensions out, and the reason is that we want to give the capability for users to select, or rather developers maybe, to select features that they want for a specific agent. Command and control, as defined by our Apache wiki pages, is a protocol that allows you to control the agents. If you were to implement these API calls, you could control your agent, and also the agent will report what it has embedded within it through an agent manifest. A lot of that's defined within C2 and core. Now we can see that the agent's built. We're completing the tests. You can skip tests, but for the purposes of this demonstration, we won't be. We'll jump into the core a little bit to kind of give you an overview of what's there. We have some controller service base classes. Logging is implemented through SPD log, which is a package in our third-party directory. We have some reporting tasks, information, repository setup. We have several persistent repositories for content, provenance, and flow files. But we also have some volatile repositories which use memory and attempt to do so optimally. State is a package that is primarily used by command and control, but this state is also defines an abstract syntax tree, an AST, for the state of the current agent. This allows us to use this not only in C2, but in other parts of the agent that help us kind of bring that vision of what's occurring and what will be occurring. YAML is just YAML classes. Finally, before we go back to the agent build, I wanted to call it the class loader. A lot of what we've built in the CMake, you'll see, is built through a variety of trying to embed all of a static library into either a binary or other static libs. And the reason for this is because we want all symbols to be built and forced into our lib or agent. This is because we use effectively what we call a class loader. It's not too different from what the JVM does and with Java. Class loaders there have a little bit more isolation than we do. Currently, we really only have a default class loader, but we do have support for multiple different types. Obviously, this requires that we inspect an object file, get the symbols, go into that file, locate the symbol, and return the location in memory or on that file where that symbol exists. This can be done in Windows and Linux, in addition to Mac OS X. The important thing to note is that there's a cost in doing so. You must pay the lookup cost, and generally this isn't done on every invocation of or instantiation of an object. It's cached as much as possible. But the reason why we include all of those symbols is so that the linker doesn't optimize out symbols that we don't have. So in this case, we're effectively, for processors or extensions, we're telling the linker that we must have all symbols to continue. So what we've built in the build directory, we have a main, we have our agent, which we could run, but in this case, there's not much to be run. We also can run unit tests. Hopefully they pass for this demonstration. In this case, there are only 50 or so tests. We have many more tests that are excluded because I only selected a small set of Bootstrap extensions. I do have a test failure, and that's because I'm running something that's colliding with a port in that test. I'm going to go back and rerun Bootstrap. I'm going to say M to enable all, disabling TensorFlow because I know that I don't have the libraries. It'll attempt to install them, but it may not be successful. So for the purpose of this, we'll exclude TensorFlow. And we can see that obviously there's a lot more work that's done because what the Bootstrap is doing is passing in the arguments to say enable all of these extensions. And so it takes a good bit longer to set up the build process and run that build process. Luckily for me, I already have a lot of things installed on this box, and I'm reasonably certain that I shouldn't have to install a lot of dependencies to get this up and going. Sorry, I didn't change directories. Now as we go into the build, obviously it's going to take a lot longer. We can see that we're building MQTT libraries now, libarchive. We've effectively enabled everything, and it's taking quite a while. It'll take quite a while to build this. So in addition to the directories I've mentioned, we also have Docker support, which you can run. You can run make Docker, which is one of our targets. Another important directory is blocks. Blocks contains some of the building blocks that we've built for being able to write your C agent. So, for example, in this case, we have in the comms block a simple function for transmitting to NiFi in C that takes into account getting all flow files, waiting on callbacks to ensure that we've completed, and utilizing potentially C2 to dictate when we should stop. The importance of this, and really the only reason we have some of these blocks, and we have many more in the roadmap, is because this enables us to build and create building blocks that can be put together. So I'm not sure in this case if I have everything. I don't have the, I'm on a different branch, so I'll actually, there we go. I'll change branches and kind of show a little bit of the work that's being done. This isn't the most up-to-date example. Let's see, find the branch. I'll change branches. That should give me some up-to-date examples. So here we have an example. This is something, this is a pull request that currently exists. This enables us to tie into the C API pretty easily using C types in Python. Here we have a processor written exclusively in Python that is actually running in our flow. So utilizing the C API, these building blocks, we're able to create a MiNiFi instance of the library, not necessarily the agent. The difference there is that the agent contains, again, the flow controller and a lot of threading, a lot of capabilities that we don't need here, such as persistent repositories, if those are built. But we do have the ability in future versions of this to run that agent in Python if we want. In this case, it's almost a custom built agent that puts these building blocks together to implement a specific flow. It's again written very quickly. We can call up the processors that exist within our build. So in this case, we're chaining get file with this get file printer processor that adds an attribute. It's pretty easy to run. We can, in a future video, I'll show some examples, but this Python directory is something that's coming, which uses all of these building blocks and all of libMiNiFi to be able to write custom executables or agents within Python. I hope this quick overview has given a little bit of information on our build process. In another video, I'll go through some of these other shell scripts in a little bit more detail on how we bootstrap. I just wanted to give a quick overview of the layout of the code and the build process. Thanks for watching.